Section: Introduction. In this section, we address the challenge of aligning large multimodal models, LMMs, especially in tasks involving video instruction following. Despite recent advancements in reinforcement learning, RL, and other techniques that have been effective in guiding LMMs to generate better content, their effectiveness in multimodal contexts is limited. The main issue is developing a robust reward system that can distinguish preferred responses from less preferred ones, especially when these responses are based on video inputs. The challenge is further complicated by hallucinations in generated content due to the lack of alignment data across different modalities. While human preference data is valuable, it is difficult to scale due to its cost and labor-intensive nature. Existing approaches for distilling preferences face scalability issues, especially for video inputs that require analyzing multiple frames. To tackle these challenges, we introduce a cost-effective reward mechanism to evaluate the quality of responses generated by video LMMs. We propose using detailed video captions as a proxy for video content, allowing a language model to analyze video content and assess the accuracy of an LMM's response to a question, as well as detect hallucinations. The language model provides natural language feedback and generates a numerical score for reward, creating a cost-effective feedback system. To ensure the effectiveness of this process, high-quality video captions are crucial. To address the shortage of such captions, we have created a comprehensive video caption dataset, SHAREGPTVIDEO, using a novel prompting technique with the GPT-4V model. This dataset contains 900K captions covering various aspects of video content. By utilizing this video caption dataset, we confirm that our reward mechanism aligns well with evaluations from the GPT-4V model-generated rewards. We train LLAVA Hound DPO using this reward mechanism and achieve an 8.1% accuracy improvement over the supervised fine-tuning SFT model. This represents a significant advancement in video LMM alignment and the successful application of a distilled preference optimization DPO method in this domain. Our contributions include developing a large-scale video caption dataset, introducing a cost-effective method for evaluating video instruction following tasks, and demonstrating the effectiveness of DPO in improving model performance for video QA tasks. Additionally, we discuss related work on large multimodal models, video text datasets, and preference modeling for LMMs. Section Summary. In this section, we address the challenge of aligning large multimodal models, LMMs, in video instruction following tasks. Despite advancements in reinforcement learning and other techniques, the effectiveness of guiding LMMs in generating accurate content remains limited in multimodal contexts due to challenges in developing a robust reward system. To overcome these obstacles, we propose a cost-effective reward mechanism using detailed video captions as a proxy for video content, enabling accurate evaluation of LMM responses and improving alignment. This approach, validated with a comprehensive video caption dataset, leads to significant performance improvements in video LMM alignment, showcasing the effectiveness of our proposed method in enhancing model performance in video understanding tasks. Section: Method. In this section, we enhance video LMM alignment through the DPO method using rewards from a language model, as shown in the illustration. We explain how we create a video caption dataset in the caption distillation subsection. Then, we talk about generating video instruction data and fine-tuning our model in the subsequent sections. Lastly, we delve into how we incorporate generated captions as feedback for the DPO method to improve our model's alignment in video instruction following tasks. For detailed video caption distillation, we select videos from 3 sources: WebVid, Vidal, and ActivityNet datasets, totaling 900K videos. To adapt to GPT-4V's image-only input requirement, we extract 10 frames per video and concatenate them into a sequence. This sequence acts as input for GPT-4V to generate a coherent caption based on the frame sequence, considering various aspects like temporal dynamics, world knowledge, and object attributes to understand the video contents comprehensively. In generating video instruction data for SFT, we follow a similar approach to Video Chat GPT. We randomly sample captions from the datasets and use Chat GPT to create question-answer pairs based on the detailed video captions, resulting in 240K instruction data for fine-tuning. This ensures factual consistency between the instructional data and the detailed captions. To provide feedback for the DPO method, we use detailed video captions to generate reward data efficiently. By selecting a subset of instruction pairs from the SFT dataset, we use ChatGPT to evaluate responses and assign a numerical reward score based on factual alignment. This process results in approximately 17K training instances for DPO. The dataset is represented as D_DPO equals V X Y_W Y_L, where V is the video, X is the question, Y_W and Y_L are positive and negative responses. The DPO objective involves optimizing the policy model pi_theta and the base reference model pi_text ref, both initialized with SFT weights, using a logistic function and a set value for beta. Our method of using detailed captions as a substitute for video frames for reward assignment proves to be cost-effective and efficient, costing less than 20. In contrast, traditional methods of preference data collection required significantly higher expenditures. Section Summary. In this section, we enhance video alignment using the DPO method with rewards from a language model, constructing a video caption dataset and discussing the generation of video instruction data. We refine our model's alignment in video instruction following tasks by incorporating generated captions as feedback for the DPO method. Our approach leverages detailed captions as a cost-effective and efficient way to generate reward data for DPO, offering a more scalable solution compared to previous methods. Section: Assessment of Evaluator with GPT-4V Caption as Evidence. In this section, we assess the effectiveness of our reward assignment method by comparing it with the GPT-4V Video QA Evaluator. Both methods follow the same scoring guidelines. We analyzed 200 videos from WebVid, Vidal, and ActivityNet datasets, each with one question and two model predictions from our SFT model. GPT-4V assigned average scores of 3.5, slightly higher than ChatGPT's 2.9. The Pearson correlation coefficient of 0.47 indicates a moderate positive correlation between the two evaluators. Most ChatGPT scores were within one standard deviation of GPT-4V scores, and their preference agreement exceeded 70%. Our video LMM is based on video LLAVA, using a language-bind encoder, MLP projector, and Vicuña language model. We trained the model in stages: caption pre-training, SFT, and DPO training. Experiments were conducted on 8A100 GPS. Model performance was evaluated on MSVDQA, MSRVTTQA, and TGIFQA datasets using ChatGPT version GPT 3.5 TURB00611. We found that different ChatGPT versions affected absolute scores but did not change the overall model ranking. We chose GPT 3.5 Turbo 0613 for its similarity to the reported scores in the video LLAVA paper. Our baseline selection included models like Video LLAVA, Video Chat GPT, Llama VID, 7B and 13B, Frozen Bilm, Video Chat, and Video LLAMA. We prioritized models with reproducible code and checkpoints to ensure the replicability of our results. Section Summary. In this section, we assess the effectiveness of our reward assignment method by comparing it with the GPT-4V Video QA Evaluator. By sampling videos from various datasets and analyzing the scores assigned by both systems, we found that GPT-4V tends to give slightly more positive evaluations, with a moderate positive correlation between the two methods. The majority of ChatGPT scores align closely with GPT-4V scores, indicating potential applicability of our benchmark in video QA evaluation, while suggesting areas for future research to enhance alignment between different evaluation methods. Section: Results. In this section, we analyzed the performance of different models in our study. We found that Llama Vid 7b and Video LLAVA have similar performance, while Llama Vid 13b performs the best. Our LLAVA Hound SFT model performs similarly to Llama Vid 13b. When we included preference modeling, LLAVA Hound DPO achieved an average accuracy of 70.75%, which is 8.1% higher than LLAVA Hound SFT with an average accuracy of 62.65%. Additionally, LLAVA Hound DPO, with the help of DPO, showed better accuracy compared to VLM-RLAV's performance achieved through reinforcement learning. In terms of error analysis, we provided examples where LLAVA Hound SFT made mistakes in describing videos, while LLAVA Hound DPO gave more accurate results. We also highlighted issues in the current benchmark, such as grammatically incorrect questions and limited single-word answers, which make it challenging to evaluate models that generate long-form text. To address these limitations, we proposed a new evaluation method using detailed captions to generate test questions for videos in benchmark datasets. This new evaluation allows for a more comprehensive assessment of model responses. Our evaluation showed that Video LLAVA performed the best among the baseline models. We also compared the performance of models trained with different methods and found that training with Video QA could improve generalization capabilities. The quality of our generated QA was comparable to existing Video QA datasets. We observed that unfreezing the MLP during training led to a decrease in performance, but the model still outperformed the baseline. Using a smaller learning rate resulted in decreased model performance, indicating the importance of finding optimal hyperparameters. Furthermore, we explored the effectiveness of self-play methodology for training and found that introducing a reward model could be more beneficial. We also analyzed the impact of training epochs on model performance and compared the use of DPO as a ranker versus a generator for candidate answers. The results showed that the DPO model had stronger generalization capabilities in answer generation, despite being trained on reward classification loss. Section Summary. In this section, we compare the performance of various models within the SFT framework, highlighting that Llama Vid 13b achieves the best accuracy. We introduce LLAVA Hound DPO, which outperforms LLAVA Hound SFT by 8.1% in accuracy, showcasing the effectiveness of incorporating preference modeling. Additionally, we propose a new benchmark evaluation method using detailed captions to address limitations in existing benchmarks, aiming to enhance the evaluation of long-form text generation models like Video LMMs. Section: Analysis on video captioning ability from pre-training. In this section, we analyze the video captioning ability of different models using various datasets containing a total of 900K distilled data instances. We use GPT-4 volts for self-evaluation to see the best possible performance and Video LLAVA as a baseline for comparison. Video LLAVA is trained on 54K Video QA data instances, while our initial checkpoint, using only 10% of the data, is trained on 90K high-quality caption data instances. This difference in training data likely explains the performance gap in the video captioning task. Our findings show that including more distilled data improves the model's performance on both familiar and unfamiliar datasets. However, there is still a performance gap compared to the GPT-4V model. We also assess how well the models can adapt to specific subsets of data, as illustrated in the appendix. Different subsets present varying challenges for generalization, with datasets like WebVid needing less data for training compared to Vidal, which has more dynamic scenes and diverse video themes.